My background is I've been doing air to water for 3 or 4 years. So I've got a lot of experience working with air to water. Paid a lot of tuition, found some stuff that didn't work, found a lot of stuff that did work, and just kind of been refining it ever since. I've got probably at this point 20 something air to waters out there in the world.
Take a step
in this,
right.
I'm also not a presenter, I'm a contractor. So this is kind of a new thing for me. So yeah, I've got probably 20 something air to waters, a few geothermal water to waters out there. I prefer working with water whenever possible. There are some very significant advantages to working with water versus working with refrigerant, especially as, if you guys don't know, refrigerants are changing. The rules around refrigerants are changing. The new refrigerants are mildly flammable. I don't say that to scare people because they're pretty hard to light. You can get them to go, but you got to put some effort in to do it. So my recommendation would be not to do that. But we're changing refrigerants again. We're going to more flammable refrigerants in about 10 years. And so the further ahead of it you can get, the better off we're all going to be. Also, as we change to the more natural refrigerants, our efficiencies are going to go up dramatically. R290 is ridiculous. I'm convinced the only reason we don't have it here is because it would put the fossil fuel industry out of business. And then politicians wouldn't make any money. Getting into the actual technology, everybody here knows what a heat pump is, I assume, so we don't have to start at that level of basic. Essentially what we're doing is we're moving energy around. We're not producing any energy. We're not burning anything to make heat. We're not creating cold energy. There's no such thing as cold energy. It's just a lack of heat energy. We're moving energy around from a place where we don't want it or a place where we want more of it. We're just moving it. We're not making it. And so with that, with an air to water heat pump, instead of what we would traditionally do is move energy through a refrigerant and put it into an airstream someplace else in a building, or take it out of a building and put it outside where it doesn't matter, we're moving it and putting it into water. Major benefit to that is that we can store energy. We also don't have to worry about freezing coils, things like that. So we get really great.
Dumb clarification. And when you say we're moving, we're taking the energy and putting it into water, whereas like traditionally we're taking the energy and we're putting it into a refrigerant.
Mm-hmm.
Also in a line set.
Yeah, so traditionally with like I said, a mini split system, let's say we have a Mitsubishi, or pick your brand, doesn't really matter. We're absorbing heat into the coil, the refrigerant in the coil, we're moving that refrigerant and we're rejecting that heat someplace else into an airstream. So we might be taking heat from, during the winter, we might be taking heat from outside, absorbing it into the refrigerant in the outdoor coil, moving it to the indoor coil and rejecting it to the house via an airstream, which works. We've been doing that for decades, especially if you get into Europe. They've been doing it even longer than we have. It works, but there are better ways to do things, right? Like everything. Building science has come a long way. We're not stick building 16 inches on center, throwing a little bit of fiberglass in it and sealing it up anymore, right? We have much better ways of building homes. Now we have much better ways of moving heat around. So a few advantages to air to water. The biggest one, especially as we change refrigerants, is that if this is my heat pump, this whole thing is outside. There is no reason to have refrigerant in the building anymore, right? And so the major benefit to that is that it doesn't really matter what they do with refrigerants. If they make them, if we switch to R290, we have very flammable refrigerants. Who cares? It's outside. That's not inside. It's not like we're pumping 300 PSI of propane through a thin wall copper tube into somebody's house. That's very problematic. But in this case, all the refrigerants outside, we're putting that energy, we're sending a water glycol mix outside to be heated or cooled. We're bringing it back inside. We can put it into a series of tanks. We could have a hot tank in the wintertime. We would be heating a hot tank. In the summertime, we're going to be chilling a cold tank. We can also do domestic hot water. Mini splits can't do domestic hot water, but we can do that pretty easily with air to water heat pumps. We also get into some options of storing energy. So in terms of heat pumps, right? Who doesn't want to lower their, who doesn't want to do a heat pump job for less money, right? Nobody's ever told me that I need to be more expensive when I'm bidding these jobs. Usually people want me to try to be less expensive, right? So when we're talking about air to water and we talk about the way a load in a building works, right? Let's say we have a building that has a 4-ton load on it for heating. That building only needs 4 tons 2% of the year. The rest of the time it's going to be somewhere significantly lower because your building needs a lot more energy if it's, let's say, 5 degrees than if it's 40 degrees. So here in New England, sure, we see those 5-degree days. We see a few of them a year. Typically for a few hours overnight, we'll see a 5-degree day. Every once in a while, we'll get a longer stretch. We might see 5 for a day, 2 days. And then the temperature breaks, we'll warm up into the teens. And then we need less energy. Well, so with air to water, what we can do is we can store energy either in a buffer tank. So these are drawn as buffer tanks, but there are also thermal storage batteries available now that will store energy for us for a longer period with less loss. I've become a big fan of these. I have 2 of them in my basement, and I can tell you they just don't leak any heat. I get them warm and they stay warm. I went on vacation for 9 days. My 160 gallon equivalent hot water went from 144 degrees to 142 and a half in 9 days. So losses are very, very low. Boiler and heat pump. I have an air to water and I have a backup boiler. They were both shut off at the breaker. It didn't recharge. There was no way for it to recharge. It just didn't lose anything. So we can store that energy. And in storing it, we could say, just as an example, this building here has a cooling load of, I want to say it's like 2.5 tons. We could, in theory, put in a 2-ton heat pump here. That's going to get awful annoying. Thanks, Josh.
I'll take turns coming.
There you go. We can all, everybody's just going to, it's a touch screen. Just reach your hand over and give it a little poke.
Back from getting pizza when it's nice and greasy.
Yeah, make sure you do it then.
Smear it on the screen.
Yeah, write me a note on the screen with grease. That's my favorite. I'll read it later. All right, so we can store energy and we can use it later on. So as an example, this building has a 2.5-ton cooling load, but if we were to put a 2-ton heat pump in here, we could make up that capacity on a battery because most of the time this building it only has a 2.5-ton load. Literally 2% of the time is what we designed to. The rest of the time the load is sub 2.5 tons. So we could put in a smaller heat pump, make up the deficit using either a buffer tank or a battery, and be able to then draw the additional energy we need, the deficit of energy we need from the battery at the point in time that we need it, without having to go and put in a bigger heat pump. I'm designing a 30-ton building in Boston, but it's a performing arts center. It only has a 30-ton load 2 hours a night and 2 hours in the afternoon when they're doing performances. Outside of that, the building's like a 10-ton building. And so what we're doing is we're looking at using a lot of these batteries because then I can put in 10 tons of heat pump instead of 30, pretty significant savings in equipment. And I don't have to worry about it because again, maybe we have a long performance and it's 3 hours a night and they do a matinee for 3 hours. That's 6 hours of the day that I have full load. And I can make that difference up by storing that energy in a battery, essentially maintenance free. That's all right, there's nothing on this.
I don't know if this question makes sense, but like how big a tank would 1 ton of battery do?
So 50,000 BTUs of battery is about the same size as a 40,000 BTU gas furnace. So we're talking about, it's about this tall, it's about this wide, and it's about this deep. I get some pictures. They're not on the computer, but I can show you some pictures later on. They're not very big. They are heavy. They're not a lot of fun to move, but they're...
It's like a teeny tiny, it's like a small like water tank.
It's smaller than that. It's literally the size of a 40,000... It's like a big...
If we were at Josh's house, what would the size compare to the ones that were...
Josh's are 60 gallons. They're 60 gallon equivalents. The 80 gallons are about 4 inches taller. All other dimensions are the same. Except weight. They go up about 40 pounds, give or take.
You say they're not fun to move, like because...
Just because of the weight.
But is it filled with water?
No, it's filled. It's a sodium nitrate that's in it.
Okay.
It's a sodium battery. So they weigh between, the ones at Josh's house weigh 471 pounds. The 80-gallon ones weigh 513.
Is that accurate? Is that the way?
Yeah.
So anything else?
This is a similar material to what's in the batteries. So right now we can see this is room temperature. You'll just have to take my word for it. This is room temperature, but there's a ton of energy stored in here in latent form. When I crack,
They're like the
like the hand warmers.
hand warmers.
Yep, exactly. So I've just cracked this. Now it's giving off that heat, so it's getting warm. You can see it's changing color. It's just rejecting that heat that was stored in the latent form. The batteries work exactly the same way. I'm not going to toss this back because I can't throw at all. I'll end up hitting somebody. Who wants to? Somebody want to feel it? I can do it without hitting somebody.
There's no water in that?
No water in that. So the battery will hold about 3 gallons of water. There's a water coil in it.
Is there some kind of gel in there that holds the sodium nitrate, or what is?
It's just so essentially it's a square bucket of sodium nitrate with 2 water heat exchangers in it.
Solution of water and sodium nitrate.
It must have some water in it.
Yeah.
It's in there's water in the. I'm sure there's water in the sodium nitrate,
Like the concentrate.
but the sodium nitrate is a chemical. Yes.
To clarify, it goes from a solid to a liquid.
At a high temperature.
So as being a solid, it's not going to have a lot of water in it. It becomes more of a solid, and the whole point of the thermal battery is to change from solid to liquid.
You're melting it.
And what we
Exactly.
talked about at my house was it's almost like molten rock.
That's me.
Right?
It's-
Take molten rock, put it into a container, heat it to where it becomes liquid, and then turn off how you're heating it and let that thing just sit for a while. It's going to stay hot for a really long time. If you run water piping through there, it's going to give off that heat to those water pipes.
Exactly.
Over time, right? And as that starts to give off heat because it was molten, it was liquid lava, as it gives off the heat to the pipe, it's going to re-solidify to a rock, right? Now that changes changed back, and it's given off its heat, and it's changed phase. And then if you heat that rock again and turn it into molten lava, it's going to be a battery again. So that's how
this
these
was
work.
hard when he threw it to you.
No, it was soft when he threw it to me.
Oh, was it?
It's yeah.
All right.
It gets hard as you heat up.
Than that, because the phase change is more of a gel to a different kind of liquid.
That's not actually the material that's in the battery. It's just a similar process is all it is. So what happens is we can store that energy, and we can either, it does a few things for us. It reduces the return temperature back to the heat pump, which boosts our COP. Anytime we can keep our supply temperatures lower, it's better. We'll get to that a little bit later on. But essentially what's happening here is we have our heat pump. It's outside the building. I've remote located these anywhere between 200, and I did a site in Lincoln that's like 200 feet away from the house. So they can be, you can really put them anywhere. You do pay an energy penalty if you put it 200 feet away because you need a pretty significant pump to push that, but it can be done. So you get your heat pump. It's outside the building.
I'm gonna help you with this.
I appreciate that. Heat pumps outside the building. We're pumping water glycol out to the heat pump. We're heating or cooling that water based on seasonality, or if we're doing domestic hot water. And then we're pumping it in and we're storing it somewhere, either in a buffer tank or a thermal battery. From there, if we have a hot tank, we have a circulator. It's just like a boiler system, like we've been doing for literally hundreds of years. We'll have a circulator pump. We can have multiple circulator pumps. That's not generally my preferred way of doing things. I like using zone valves because when we do zone pumps, we end up over pumping everything. It's an inefficient way of using the energy. But we'll have a circulator pump, and we can go through zone valves. These are just examples of different ways we can do it. We could do a radiant floor. We could do high mass baseboards and panel radiators. I've even done a couple jobs with cast iron. Now, whenever we can, when we're working with heat pumps, we want to try to lower our outlet water temperature because we get higher COPs. COP is a coefficient of performance. So what that means is if we're putting 1 watt of, with an electric heater, an electric baseboard heater, right, or a space heater, if I put 1 watt of electricity into it, I get 1 watt of heat out of it. That's a COP of 1. If I have a heat pump that has a COP of 3, What that means is if I put 1 watt of power into that heat pump, I get 3 watts of heat out of it. Not because it created heat, it's not making any heat, it's just able to transfer heat that efficiently from outside to inside. So the next biggest question I get is this is New England, it gets cold. We've seen minus 13 here on a few occasions. How on earth do we get heat at minus 13 from outside and move it into the house? Well, that's because absolute zero is like minus 428 or something like that. Minus 473. That's really cold. There's still a hell of a lot of heat in the air at minus 13 or minus 22, which is what these heat pumps are all rated to. And as long as we can make the coil temperature outside lower than the outside temperature, heat will naturally flow from the outside air, let's say it's 30 degrees, to the coil that's 0 degrees. Or from the outside air that's 0 degrees to the coil that's minus 30. So as long as we can make that outdoor coil here colder than the air outside, heat will naturally flow. So now all we're really doing is we're running a compressor to move that refrigerant around, and we're moving a couple of fans to pull air from the outside across that coil so that we can steal that heat. From there, that like I said, that heat is put into the water, which will flow to our tank. So a few things that we've learned through installing these is, hey, we got to think about this rationally, right? Hottest water is going to sit at the top of a tank. So if we have a heating tank, we want to make sure that we're feeding into the top of that heating tank and we're pulling out of the top of that tank. We want to get the hottest water we can out of it. No point in cooking water hot if we're going to pull out of the bottom where that water is the coldest, right? We want to make sure we're pulling from the top of the tank going out to our heating systems. Another thing that does for us is that if we're pulling out of the top, we're returning down to the bottom of the tank. That means our heat pump is always going to see the coldest possible water going back to it, which is going to boost our efficiency. Again, this is all about maximizing our energy use. We want to be good stewards of the energy that we have, that your client or you, if you're the end user, is paying for. We don't want to be wasting it. So we want to make sure that the heat pump is set up for success. Vice versa happens in cooling. If I'm in cooling, I'm going into the bottom of the tank and I'm drawing from the bottom of the tank because I want to make sure that I'm pulling the coldest water possible and I'm not having to over chill that tank to be able to accomplish my air conditioning.
Those batteries work equally effectively storing cold temperatures as hot?
Negative. So the batteries are designed for heating. You would get a heating or a cooling battery. So in cooling mode, a heating battery is just going to perform like the volume of water. So that salt nitrate, the volume of salt nitrate that's in there, behaves like water. It's just storing sensible. In New England, because we're a heat-centric climate, most of the time, passive can kind of throw a wrench into that. But generally, most houses that we work in New England are going to be heat-centric homes. They're going to have higher heating loads than cooling loads. So you would put in a heating battery and you would just use it for the sensible and cooling. That generally works out just fine because these units, all of these heat pumps, I've got experience with SpacePack. I have experience with Stiebel Eltron, Enertech. Those are the 3 that I've worked with the most. I actually have my own heat pump line that's coming out. It's not available yet. But all of the heat pumps that we're dealing with, that in my experience, have really good turndowns. So we can really drop that load and just match the cooling load pretty well.
What is turned down?
Turning down would be like, let's say I have a 4-ton heat pump, so it can output 48,000 BTUs on the high side. The turn down is to say how low it can go. So my 4-ton heat pump can drop down to 1 ton. So it can go it will match load somewhere between 12,000 BTUs and 48,000 BTUs. I have a 60,000 BTU that can be a 66,000 BTU, or it can be a 13,000 BTU, and somewhere in between based on what's needed in the house.
So, in other words, in the shoulder season, like right now, where you don't need a full 48 or 60,000 BTUs, you're still getting those higher efficiencies even while the unit is producing less than its rated capacity.
Exactly. So we actually see higher efficiencies when it's modulated down. So it's to your benefit to have it. It's actually, so we kind of flip this on its head, right? Because everybody here has probably heard, don't oversize your heat pumps, right? Oversizing heat pumps generally leads to short cycling, terrible dehumidification, shorter life expectancy, everything bad that you could imagine for your HVAC system generally stems from the heat pump being oversized. But again, we live in Massachusetts, right? So our heat loads in a typical home, not a passive house, but typical home, our heat loads are going to be somewhere between 2x and like 1.5 and 3x the cooling loads, depending on the house, right? And we're sizing these things for primary source heat a lot of the time. Well, how's that going to work? If I have a 70,000 BTU house, I'm now putting in, I'm realistically putting in 10 tons of heat pump in a 70,000 BTU house because heat pumps all derate when it gets cold. But your client or you, if you're the end user, you don't want to hear that, well, your house isn't going to reach temperature because it's cold outside. That's when you want it to, you don't really care if it doesn't get to temperature in the spring or the fall. You open a window, right? But if it's 0 degrees outside, you want your house to be warm. So we're realistically putting in 10 tons of heat pump. But that same house with a 70,000 BTU load might have a 30,000 BTU cooling load. That's not even closely unrealistic. Those are very, very reasonable numbers that you would see. So now you're way oversized for cooling season. What the hell are you going to do with that? Your house isn't going to dehumidify. You're going to put in a supplemental dehumidifier, great product. Santa Fe is an awesome product. April Air too. But that's a whole nother piece of equipment you've got to put in. You've got to maintain it. You've got to change filters on it. There's just a lot that you need to do with that. And if you go with an air to water, you can have that big heat pump. All it's doing, all your heat pump actually, oops, that's the wrong button. All your heat pump actually cares about is your tank temperature. So now if your distribution, you can have separate distributions, right? I can have a heated floor and that can be designed around 70,000 BTUs for that house. But I can have a couple small cooling only minis. Well, they wouldn't be cooling only. They'd have the ability to do heating as well. But in this case, you'd be using your mini splits for cooling or a fan or a hydronic air handler for cooling, something along those lines. And you can be right sized for both times a year. I do a lot of work with Space Pack air handlers and actually the iFlow air handler that Steve's company, the folks who are sponsoring tonight, they both have they have adjustable air speeds based on what you're trying to do. So I can have enough air to push 70,000 BTUs out of the same exact air handler as I'm doing 30,000 BTUs of cooling. So I can be right sized in both seasons. I don't have to deal with the call that I'm not dehumidifying, I'm short cycling. My heat pump comes on, it runs for 3 minutes, it cools my space down, and now my room is 70 degrees with 70% humidity, and it just feels nasty, right? These houses, they're going to be right sized really regardless of what happens. And as far as heating season goes, this tank, it's a hot tank. I get a turn down ratio. I can just not heat that tank as hot. I can run an outdoor reset, so I can tie my water temperature to my outdoor temperature or even to my indoor temperature. So as an example, I need more heat in a house if it's 0 degrees than I do if it's 50 degrees or 40 degrees, right? This heat pump knows what the outdoor temperature is. It physically sits outside the house. It's got a sensor. It knows what the temperature is. It will adjust. We can program these to adjust the temperature of this tank accordingly so that I might cook 120 degrees if it's 0 degrees outside, but on that 40 degree day, maybe I'm only cooking to 80 degrees because I don't need that much heat on an 80 degree day to heat a house. And if I'm pushing 80 degree water, I'm getting pretty close to 80 degree air. That's enough to keep the house warm pretty easily. We can even technically go lower, though we don't want to go much lower than that because surface area of your body is about 87. And 80 degree air, even though it will warm the space, is going to feel cool on your body. So we don't generally want to go much below that.
So seasonally, you can adjust the temperature of your storage.
Yep. Well, you don't have to. It'll do it automatically.
Yeah. But that's what it's doing. So
Yep.
That makes a lot of sense. It'd be like if somebody likes a shower hot and somebody likes a shower just warm, and your hot water tank new, to just heat it to whichever temperature.
Yeah. I'm taking a shower and I want it to melt my skin off, so we're going to cook water hotter. But my girlfriend is taking a shower and she wants it to be mild. We don't have to heat it as hot as for me. Your house your heat pump is essentially doing that for your house. It's saying, it's not that cold outside. I don't need to cook water and burn all this excess energy. So why would I want to do that? And it reacts accordingly. So they're great in terms of energy efficiency. They're also nice because we have one piece of equipment outside, and we're able to do cooling in the summer, heating in the winter, and do domestic hot water. And in some applications, we can actually recover when we're doing air conditioning. So again, in air conditioning mode, we're not creating cold energy. We're just removing heat energy from the house and putting it outside. In some of these applications, we can actually recover 30% of that energy that we would normally just be spitting outside because it doesn't matter, and we can put it into your domestic hot water. So as long as you're already going to be running your air conditioning, you can get your hot water out of it. Now, I'm not allowed to call it free hot water because you're still expending energy, but it's the same energy that you were going to be using anyways to cool the house, so long as you were in fact going to be cooling your house. For the weird people who don't like air conditioning and want their house to be 95 degrees, then you're going to have to run it in heat mode to make the hot water. There's no two ways about it. But for most people, most of my clients want air conditioning, and here's a great way to really pull double duty with that energy that we're spending. Again, it comes back to being a good steward of the energy that we're creating and using.
Jason, just for those of us, like, I don't operate day to day in the HVAC space. I'm looking at this diagram, imagining that your return lines going through the tank are diluting the tank, right? If I have hot water in the tank and I bring
your return line back?
Yeah, why not bypass the tank and go right to the heat pump?
So, because what'll happen a lot of the time is that there's still, like, let's say we're dealing with a radiant floor here, right? Now I'm going to be returning cold water back to the bottom of the tank. But this radiator, that's not, because there's going to be some mixing going on here. This tank, in theory, would be, because I have cast iron on it, this tank would be 140 degrees. So this I would want to bypass and go straight back to the heat pump. But this here, there's still a heck of a lot of usable energy coming back. Yep. And that heat is going to rise up in the buffer tank. Essentially, a buffer tank is just a way it separates the heat. So the water heat transfers really well through conduction, which is surface to surface contact. So those water molecules coming back, they're in physical contact with the water molecules in the tank. The heat's going to transfer and it's going to move. You're going to get some mixing.
Well, also talk hydraulic separation.
It's literally, it's called hydraulic separation. But your hottest water is going to rise. You're going to see if this tank's 140 up here, it could be as low as like 115 down here. And we can actually recover some of the heat through the return side here and just recycle it. Whereas this corner here, this is going to be the coldest section of the tank. Assuming the tank is, I've seen some really goofy buffer tank setups from like random manufacturers out there. MB Tuck has one that I just can't make heads or tails out of why they even made it. It doesn't make any sense at all. But by and large, most of these things are designed fairly well, and you're still gonna get cold water here because you have a suction here, so you're creating a negative pressure up here. You do have a negative pressure here, but you're coming in and you lose velocity coming in because you're coming from a pipe that's 2 inches in diameter at the biggest, and you're going into a buffer tank that's this big around. So you lose all your velocity. The coldest water is going to settle to the bottom, get dragged across the bottom of the tank. The warmer water that's coming back is going to rise up, pool at the top, and get pulled back through to go around the ride again, go around that roller coaster one more time.
Hydraulic separation is a key function, though.
Yeah, because you need to break out your different flows.
And if you're not familiar with that concept, then it's important to talk through why you need a buffer tank at all.
The other thing that you need the buffer tank for is, and this is a little more high level, but this is going to be a pretty big pump. We're talking about moving generally 12 gallons a minute minimum. But my distribution pump here, I try to use a lot of variable speed pumps so that if I don't need a lot of flow, my floor or my radiators, they're at temperature, I might only be pulling 2 gallons a minute from here. If I didn't have this buffer tank, now I have to pull 12. My heat pump won't run if I push less than really 8 gallons a minute through it. My heat pump will go and give me all sorts of errors. It'll have a whole bunch of temper tantrums. Nobody's going to be happy with that. So I need a way to guarantee that I've got my 12 gallons of flow moving from my tank to my heat pump and back to my tank. And this just gives me a volume of water here so that I can spit water in here and I always get the full volume I need back through the return, regardless of what's happening on this side. Whether I'm pulling 2 gallons or 14 gallons, it doesn't matter. And on the other side of it, maybe my radiant floor and my cast iron loop just kicked on and I've got a really big draw. I might be pulling 14, 18 gallons a minute. Well, that's where my storage is going to come in. I've got some extra storage built in here. I'm pushing 12 gallons a minute through here. So I've got some buffer to catch up before I start to lose ground in my tank and my tank starts to cool. So there's a few different things at play here, but the buffer tank, it does 2 things. It gives me my hydraulic separation, which I need fundamentally for my heat pump to work. It also gives me a way to boost my efficiency. And then the batteries you could pipe a battery in lieu of a buffer tank. The piping looks a little bit different on that. Pete, you got to write me a note on the screen with the grease. Now I'm sad. I was looking forward to a love letter.
Why would you use a flat plate heat exchanger?
Flat plate heat exchangers don't give me the volume I need. So you could do a flat plate heat exchanger on this loop here, but then you're not going to get the. Then it's really at that point you've made it direct to load. And now what's going to happen is you've only got the volume of your primary loop and you can heat that and really short cycle this. We size our buffer tanks specifically to make sure that we're going to see a minimum runtime. And with a flat plate, you're really kind of tied to the turn down on the heat pump. Whereas with the buffer tank, I've got the turn down on the heat pump and I've got the volume of water in that tank. So that let's say this call ends, there's no call on this, but my buffer tank is calling. By the time I reach that dead band on my buffer tank, so that's usually, I set that typically to about 10 degrees. So my set point might be 130. When it hits 130, it's going to shut off. It's going to come back on when that tank gets down to 120, right? So then I've got the turn down on my heat pump and I've got potentially 80 gallons of water in that buffer tank. So I'm going to have my minimum 15 minutes of runtime to take this 80 gallons in this tank up the 10 degrees I need to make it usable for me. Whereas with a flat plate, you're direct to load. So I have to be able to transfer whenever that heat pump's running. I need a minimum load on the house of whatever my turn down is on the heat pump. So for example, if I have a heat pump that can turn down to 12,000 BTUs, but I don't have 12,000 BTUs of load, my heat pump is going to short cycle because there's no place to put that energy. So what's going to happen is my supply temperature is going to rise, my flat plate's going to get warm. Because I'm not moving that much heat on the other side of the flat plate, my return is going to rise and I'm going to start sending warmer water back to my heat pump. And it's A, going to crash my efficiency, and B, going to short cycle my heat pump. So just as a general rule of thumb, no matter what your heat pump is, air to air, air to water, water to water, water to air, doesn't matter, is not running efficiently for about 15 minutes. It doesn't get up to operating steady state for about 15 minutes. And again, it's completely regardless of the type of heat pump you have. The brand doesn't matter. The style of heat pump doesn't matter. They just don't run efficiently for about 15 minutes. They take that much time. So we want to design it so that we're going to see longer than 15 minutes of runtime, and we're going to have that load coming out of there. So ideally, I want my heat pump to, when it's hot outside, my heat pump doesn't turn off. It runs continuously in some level of modulation from, the time it gets to be 80 degrees outside till it drops to about 75 degrees outside. It might low and slow, exactly. Just like you're grilling meat or whatever it is that you might grill low and slow. Yeah, smoking something.
Sounds like, from what I'm understanding, you don't have a problem with people who want to take like endless showers. Like, it's not about the size of the tank, it's about the flow rate that the heat pump can push out. So you can.
Yeah, if you wanted to take I have a 17-year-old at home with hair down to here, and she takes epic showers. She's never going to watch this, so it's okay for me to say this. And so when you think about your heat pump water heater, right? You've got a half-ton heat pump, and you've got generally some resistance backup. Usually it's about 3 kilowatts. You don't have that much heat in that water heater to replenish that tank if you're running like a heat pump water heater. Your electric water heaters, those are 30 amps. They're maybe 6 kW. So there's not a lot of heat there. This heat pump can be 66,000 BTUs. I can replenish heat into that water heater, that water tank, pretty faster than I can deplete it generally. And if I have somebody who I know is going to take epic showers, usually you can tell because they have, I did a house in Newton and you could probably drown in that shower. There's like 14 shower heads. It's obnoxious. It's absolutely insane. I did, this was years ago, but for that, we were like, hey, look you need a storage tank and you need a big ass storage tank because you're gonna, and of course they say, well, we don't take that long. Of course you don't. You only have 14 shower heads in your bathroom for fun. You're not actually gonna use them. You just like paying plumbers. You think we should have more money and you just want to give it to us. If you have 14 shower heads, odds are you're taking long showers or you're at least using a lot of water. So like, you got to use your visual cues because your clients maybe aren't always going to be the most honest with you. So they value this, the showers. Yes.
So speaking of plumbing, so pardon me, but the piping between the heat pump and the tanks, what's it made of and how big is it?
It can be really anything.
And is it ever exposed to freezing?
It's got glycol protection. So yes, it does leave the house. So it is exposed to cold weather, which is why we glycol protect. But if this is your primary source of heat, right, it's always going to be warm because your house is going to need heat all the time during the winter. If it's below 32 degrees outside, you're heating your house. So it's not going to be anywhere near freezing. My personal house, I don't have glycol in it. Space Pack hopefully isn't going to watch this because they won't like that. That's against their warranty. But also, I'm the one who would report it, and I'm not going to tell on myself. So
It's 3/4 inch. What?
no, it's 1.25 inches. I run 1.25 inches. I also do. What's that?
Is it plastic or metal?
I like fused polypropylene myself, but you can run copper, you can run PEX. The fused polypropylene is great because it's an insulator.
Of course you would.
That's the same as cross-linked?
What's that?
No. Fused is the same.
No.
Different from cross-linked?
No, fused is an actual. It's a polypropylene pipe. You have an iron. You heat up both sides. You push them together, and when you're done with it, you can cut them in half. I used to have a sample. Do you have a sample in your car, Chris? Of the Noopy?
No.
No. I used to have a sample.
Polypropylene is one of the most benign plastics there is.
It's fantastic. It also it doesn't transfer heat. So well, it does, but not well. So it's an insulator. You can actually you're protecting your piping. It helps reduce sweating because all of your water lines in the summertime when you're running chilled water will sweat. We can reduce that by using polypropylene because it's a natural insulator. The pipe itself is an insulator and doesn't sweat as much. In certain conditions, it will still sweat, but it doesn't sweat as much. And in the heating side, we're just not wasting heat by letting it leak out of pipes. Copper pipes, for example. Give you an example. My house, I have an oil boiler as backup. I moved into my house in January. My boiler crapped out on me in February, and I couldn't do my air-to-water heat pump until May. So, and I did mention I have a 17-year-old at home who likes showers, and also a girlfriend who would probably take my head off if we went 2 months without hot water. So I put a boiler back in, and when I was done with that boiler, I piped it in polypropylene because if I'm going to do a job, I might as well do it well. And whenever I'm done with something, I'll cook it up to full temperature. So I ran it to 190 degrees. You could not hold a 190 degree copper pipe in your hand, but I could hold that polypropylene pipe with 190 degree water moving through it, not indefinitely, but for a minute or two, like a solid 120, 180 seconds, you could hold it. It got hot, you definitely felt it, but not nearly as much as you'd hold it for about a second with copper, and then you'd probably go to the sink and rinse your hand with cold water and hope you didn't burn yourself for real.
Don't try that at home.
Is that piping more expensive?
The piping is less expensive. The valving and every fitting there is way more expensive. The pipe itself is cheap, but the valves, 1.25 ball valves, about $170 for one. So you end up all the money you saved in pipe, you burn in fittings. But it's a better product. It's also a forever product. It's it doesn't corrode. It's completely immune to glycol, so you don't have any issues with that. It's benign. It's not gonna leach things into your water. Not that you're likely to be drinking from it, but you could. It's rated for it. You're not gonna drink from your hot tank because it's got glycol in it. So that's a good way to get the forever nap.
What's in the domestic hot water?
Domestic hot water is strictly water.
Okay.
So what happens is in the winter, because that is a pure water line, when that temperature, if that temperature was to drop, there are electronics built into the heat pump that will say, oh, heck, my domestic hot water side, which is not glycol protected, is it's getting cold. So I'm going to kick on the pump for that, and I'm going to circulate some hot water, and it will actually, it can heat, the component that allows it to do domestic hot water is called a desuperheater. It's in line with in the refrigerant cycle, it's in line before the condenser. So it will run, it'll siphon some heat and put it into the domestic water line so that you don't have to worry about that line freezing. You could glycol protect it and put it on a flat plate heat exchanger of some sort if you wanted to, but that's more complexity. It's another pump, more wiring, more piping. Generally, you would just lean on the electronics to give you the protection.
So you'd be nervous about an extended power outage when you don't have power for the system?
If you're running DHW direct without any kind of backup, then yeah, an extended power outage could be problematic for you.
What is the difference of efficiency against like just a heat pump water heater?
So that's kind of a loaded question because a heat pump water heater, right? They have really high COPs because they live in the house, and so they're extracting heat from the house. If you've got a old cast iron boiler sitting next to it, that's great. You've got waste heat. It's not doing anything except making the boiler room warmer than you want it to be. That's a great application for a heat pump water heater. If you don't have that, if you have just an open basement, you've electrified your home already, you don't have that waste heat sitting there, now you've got to put heat back into your basement so that you can take it out of your basement and put it into your hot water. So when you start talking about moving it twice, the differences in efficiency are negligible. If you have an application where you've just got a bunch of waste heat sitting around, we don't compete, just to be completely straight with you. COP is going to be somewhere around, depending on time of year, it can be anywhere between 1.5 and 2.5, whereas like your heat pump water heater is 4. But during the winter, if you're heating your basement, most of the time you're doing it with an electric resistance heater. Most people aren't putting a mini split in their basement. If you are, call me because I want to be your contractor. If you like throwing money away, I'm your guy. I'm more than happy to help you with it. I'm just kidding. But yeah, if you're moving heat around twice, you're essentially paying the one COP from the electric baseboard to heat the basement. And then you're taking that heat and you're moving it again, albeit at higher efficiencies, but you're moving it again into your water. It's not a very efficient way to do it. Whereas we can do it directly without the byproduct of having to install a heater in your basement just to take the heat out of just to air condition the basement at the same time. They are really good for dehumidifying a basement though. So if you have a basement that's like moist, if you could take on water, that's a great way to do it because you'll dehumidify it and then the electric resistance heater will give you back the heat you need so you can dehumidify year round. If you have that kind of problem. I have a house it's not mine. I have a client who has a house in Malden and seasonally they actively have like a little river that runs through the basement. How that ever got approved is beyond me.
Just a data point. I mean, there is a formula for calculating net COP for heat pumps in series. So if each heat pump is a COP of 3, the net ends up 1.8.
That's probably a pretty close comparison because you're going to have a COP of 2, and then you're going to have a COP of with your heat pump. And you're going to have a COP of like 3.5 to 5 on your heat pump water heater, but your electric heater has a COP of 1. So they kind of balance out, and it ends up being not the most fantastic. So on a 1-to-1 basis, if you have a boiler sitting there, you're going to win with the boiler every day. But if you don't have a boiler just leaking heat into the basement for funsies, you're gonna lose out having the heat pump water heater because you got to reheat the basement. So then coming to this side of the equation here, right? What are the different ways that we can make heat, we can store heat. We've kind of covered that pretty in depth now, right? Everybody has a pretty decent grasp on that side of it. How do we get it into the house? Well, that's the fun part. How do you want to get it into the house? Because we can pretty much do it. There's the option. The best option is radiant floors because who doesn't want radiant floors? They're fantastic. I've never had somebody say no. My feet are I would rather my feet be cold, right? When I get out of the shower, I want to step on cold tile. Never happened. I've been doing this since 2002. I've never had that happen. So you can do radiant floors. You can do panel radiators if that's your jam. That's the way they do it predominantly in Europe, is a lot of panel radiators. They're fantastic. They give you room by room zone control. They're really nice. I think they're nice looking. Most people think they're nice looking. They're not bulky and intrusive. But let's say you have an old house. That's okay. We can work with cast iron. We got to put magnetic filtration on there. Well, that's not that big of a deal. Pretty easy to do. Magnetic filtration. So if we have cast iron radiators, they release, essentially they rust, and they add rust into the hydronic system. We don't want that rust. All of the pumps that, at least for me, all the pumps that I use are permanent magnet ECM pumps. So they're high efficiency circulators. They work with magnets. And so if I've got a bunch of rust in my water, that rust is going to stick to those magnets and it's going to gum them up, and those pumps aren't going to last very long. So we need a way to capture and remove that rust from the system so we don't make a mess. We don't destroy our brand new system. We don't want to put in a new system for, a lot of money and then have to come back 2 years later and say, we got to change out a pump. And then 2 years later, we got to change out another pump. Nobody likes us if we do that.
So legacy circulators are immune to that problem, or what?
Legacy circulators don't work off magnets. They are permanent split capacitor pumps. So there's no magnetics in those. They're way lower. They're about a third less efficient. Generally about 33% less efficient, but they are more rust friendly.
I've heard plumbers say that water that's aged becomes a better transporter
Or like the available
of the heat.
oxygen
Gets used.
Well, the oxygen gets depleted and pushed out through the air separators. So that's another thing. We have great air separation with air-to-water heat pumps. Each tank has an air separator on the top. So as that water flows into the tank and the velocity falls off a cliff, because we're going from at most a 2-inch pipe to a tank that's 20-something inches in diameter, we lose all of our velocity. The air, any air bubbles, even micro bubbles that are in there, will rise up, float to the top, and get ejected out from the system. So we degas our systems pretty quickly. We don't have to worry about air. But rust is a thing that we want to take care of. We want that out of our system because, again, you don't have to, I suppose, but if you're putting in a high efficiency heating system, it only makes sense to use high efficiency pumps, and we just want to protect them. The magnetic filters aren't that expensive. It's not something that you need to change. You just clean it. Your contractor should be doing it every year on the maintenance. It's very simple, very non-invasive. It introduces a little bit of air to the system. But again, we have these really great air separators on every tank that we put in. So that's okay. We're going to degas the system and probably before the guy even leaves.
Filter. Where does the magnetic filter live?
It depends on the system and how I'm piping it. In this application, I would put the magnetic filter here. I want to catch that rust as it comes back before it hits my tank. In my application, I have it on the outlet side of my cast iron oil boiler because I don't want my boiler is the only thing that's going to cause rust in my system. So I want to capture it as it leaves that. It kind of depends on where the cast iron is in the system. Your designer would be looking at your system and pretty much telling you where it needs to be if you have cast iron in the system.
Can you get temperatures hot enough out of the air to water heat pump to do like a retrofit on like a steam radiator?
Loaded question. Steam is tough because it's usually only single pipe, so there's no return. So if it's a 2-pipe steam system, sometimes you can retrofit. Technically, you can always retrofit. The radiator is the same on steam as it is in water. You just need to fight that plug out of the other side that's been there for 150 years and is really, really content right where it is. I've done it successfully like once, but it took a lot of heat and a lot of cursing. So it's not a child-friendly event. If you have kids, they should not be in the house. Yeah, it can be done. It's tough.
The size of the radiator, like if you're not getting, 212 degree,
So you are going to get a lot less BTUs out of it. But if we think about most of the houses we're working in, if you have somebody who's interested in a heat pump, and especially an air-to-water heat pump, they've probably done other renovations to the house. So the house, remember when the steam system went in, The house had single pane windows. They were probably leaving them open 4 inches every night for open air ventilation because they didn't have penicillin yet. And they had no insulation in the walls. That house leaked like a sieve. Literally, it would have been, if you didn't have the radiators, it would be the same temperature as outside. Fast forward to today, especially somebody interested in this, they've probably got, at a bare minimum, replacement windows and mass save blown-in insulation. More realistically, somebody interested in something like this, they have exterior board insulation, they have cavity insulation, they have some form of good replacement window, not just your contractor special cheapie. The contractor who did the windows actually filled in the sashes, and so they're actually fairly airtight. And so you don't need the same BTUs that you got out of the steam anymore. You've reduced the building's load. So that's how I think I mentioned earlier, I have a house in Brighton I did that's cast iron, and use the cast iron as their heating source. And no, I can't get my water temperature much above 140, 145, but that's okay because that house has new windows and insulation. And so it doesn't need to be 100. It was hydronic, but it doesn't need to be 180 degrees anymore. The 140 covers me. Gives me a really nice heating system for that house. That customer's really comfortable. So it can be done, but there's you got to do some external thinking about that, because again, if you do walk into a house and for whatever reason the bays are still empty and they have original windows, no, you can't. Not a chance. You can do it, but you'll get sued. The loads have to come down pretty dramatically to be able to get away with that. So it can be done, but it's not a sure thing.
The radiator too.
Yep. So you would want to run a flush through there, and then when you put it into operation, it was built into my price. We went back and cleaned that filter every week for a month, because we're talking about a house built in 1901. There was a lot of crap in those radiators. I'm not a big fan of running hydronic system cleaners through, because sometimes that's the only thing that's holding those pipes together and keeping them from leaking. And I don't want to be the guy who takes that away and makes a leak in the wall somewhere that nobody finds for a month when there's mold and a nightmare. So we'll just go and clean out we'll set the pump to run on high speed. We'll go clean it out once a week for a month, and it's a much safer way.
For the distribution system on the screen, could you use one tank and switch between hot and cold?
That is an option. You can certainly use one tank and switch between hot and cold. We've sort of moved away from doing that because it ends up being an energy suck in the shoulder seasons, because it might be cold enough at night to call for heat, right? So now we've got to heat this if we only have one tank, this is my only tank, I've got this tank heated. Now shoulder seasons, I might only be heating it to 90 or 80, but then noon comes around and now I get a call for AC. Well, I've got this tank, it's probably still sitting at 75 degrees. Now I've got to chill it to 45 degrees. And then 8 o'clock rolls around, the sun goes down, and now I've got a heat call again. I've got to heat it back up to 80, 90 degrees. So we just end up using a lot of energy if we do one tank. It is an option. It works. I've done it a few times. That's one of those cases of tuition. I didn't go to college, so when I make mistakes and I have to pay to fix them, I call that tuition. So that's a case of tuition for you. That's contractor tuition. The School of Hard Knocks, exactly. I don't know who said it, but I heard it.
Could the thermal battery be used in that situation?
Yep, the thermal batteries. So that's why we really like doing twin tanks where we have a hot tank and a cooling tank, and we like using the hot tank with a battery whenever we can, because then we can, shoulder season, towards the end of the shoulder season, maybe I don't need heat for 3 or 4 days. And then all of a sudden it gets cold again. I heated that tank 3 or 4 days ago, and it's still almost just as hot as it was when I finished heating it. So I don't have to pay to heat it again, and I don't have to pay to maintain it. The battery just hangs out there warm still, because that's what they do. They just don't give off any heat.
So the battery would be an additional component off the side of each tank.
Nope, you would replace the tank with the battery. So I could have instead of having a tank, I could have a battery. My air to water at my house, I don't have any pictures of it yet because the room is still in progress. It's a never-ending project of mine. I only have one buffer tank. It's for my cooling side. I have 2 batteries for my heat, 2 batteries for my hot water. And
Battery has a heat exchanger in it.
there's 2 heat exchangers in it. There's a charging heat exchanger from the heat pump, and then there's a discharging heat exchanger that goes to either domestic water or heating side. I'm gonna just flip the screen here. So we can go from mild to wild. This is actually Josh's house, where we have 2 heat pumps. We have dual pumps for each. There's only about 1 million valves here, but you can see this is actually a heating battery in this application, where we're charging in through this circuit, going back to the heat pump. We're discharging through this circuit, going to Josh had to be complicated. He had to have radiant floors and all sorts of other stuff. So we have a bunch of components here. So we go to a mixing valve, we run out, we go to his radiant floor distribution here. Come back, and in this case, we go back to the batteries. So these systems can get pretty, this is a 2-page diagram of piping. There's a lot going on in this one. We can do a lot of different stuff. So when we get to doing air to water, the look on you guys' faces is awesome. I am loving this. You should have seen my installer when I gave him this diagram. So when I say we can do, like, how do you want the heat coming into the house? And I tell you, you tell me, I can do whatever you want. Literally, I can do pretty much whatever you want. You want heated walls? We can do that. You want heated floors? Cool. Radiators? Awesome. Fan coils? We can do that. Josh has 5 fan coils in his house, right? 4? 5? 4. 4 fan coils in his house. I only did the job. I don't know anything about it. Yeah, so we can literally do all sorts of things. I have 2 batteries for radiant. I have a cooling tank. I have a heating tank down here. There's a lot going on. We can, and this is because Josh has several different temperatures in his house. He's got in-slab radiant, which is a different temperature from his warm board radiant, which is a different temperature from his heating fan coil radiant. There's a lot. So we can literally do pretty much anything. Now, the last thing I want to talk about with air to water before I'm done ranting and you guys can start talking is cost, right? We kind of alluded to this last time with Ross. Air to water is awesome, but it comes with a price tag. It's very expensive. I don't even remember what your job is, but his heat pumps were donated and it was still like $150K plus to do his house, and his heat pumps were donated. Albeit, I think I mentioned it, his house is quite complicated. He has a lot going on, and it's like 9,200 conditioned square feet. So it's big and it's complicated, which means it's expensive. Generally, they don't have to be that expensive if we're not doing, as much stuff, if we're doing just air distribution or if we're doing just radiant. And there are ways and if it's smaller and, there are ways to make it less expensive. But air to water is expensive. And I'd like to talk about that just for a minute, because when I give people quotes, a lot of times they think it's like I don't want to do the job price. It's just a walkaway price where, like, you guys who are contractors in here have probably run into a customer somewhere along the line where you're like, yeah, I don't want to do this, so I'm going to mark this up like 300%. So if I get it, it's worth the hassle of having to deal with this person. When you get high prices on these air to water jobs, that's not the case. They're just really expensive jobs. The heat pumps are almost 4x the cost of an equivalent mini split condenser, just to physically buy them. But then from there, you also have all these other components. You've got buffer tanks, those cost money. The pumps, those cost money. Batteries, those are expensive.
Is any of it free?
None of it's free. Nope.
The electric bill. That's what you get. There you go.
I'm not paying. Don't listen to him. I'm not paying your electric bill. No, everything adds up. And then on the other side of it, the labor is a lot more expensive. I'm not. Oh, look at it. It recovered though. I didn't have to touch it.
Okay.
You've been killing it. So yeah,
I was taking notes.
taking notes and trying to keep the computer screen alive. That's actually my fault because I'm not good at computers. There's probably a way to turn off the screensaver. Yeah, see, all you smart people here.
But this
All
is
you-
just so entertaining.
Yeah. It's a test for him.
That's right.
He's done so far. He's got like a 95.
Thank you.
So yeah, there's a lot that goes into this. Also the labor. On a job like this, I need a heat pump guy. I need somebody who can plumb this thing, and not every plumber can plumb this. Just
That's the heating side.
this is the heating side. This isn't the cooling side.
Can we scroll
Well,
down
that's
to the
the
cooling
sure.
side too?
I can.
Come on, Lois.
Oh no, hold on.
Wait, you click something.
Changes color.
There we go.
Oh, it's a touch screen?
It's a touch screen.
I could've
So
done this
there
the
we
whole
go.
time.
So cooling is down here. This is cooling stuff here. Goes out to a fan coil. I'm not completely done drawing it because I ran out of space and I'm trying to figure out how to.
For months.
Yeah.
I need my
I feel
drawing.
like you should have it framed ultimately at the end. Like this is a piece of abstract art.
You're gonna need some really big frames. It's yeah. I'm just trying to figure out how, it's all built now. I'm just trying to figure out how to get it all onto a diagram so it makes some shred of sense. So cooling side is your tank here, coming down to your distribution, and then from there I ran out of space, and I'm trying to sort that out.
Where like your handlers come in and all the air duct work
Yeah.
that is needed. So it's you still have to have air duct work in addition to your heating system that is hydronic. Yeah.
So-
Here, we can talk.
No.
She's like, nope, rather not. So it comes. There's a lot of different. I have a heat pump guy. I have a ductwork guy. I have a plumber who's got to be a really good plumber to do that. I have a controls guy because there are a lot of controls that go into this, and so all of those guys cost money. They all want to make a living, and so these air to water jobs. They are expensive. So what I tell people, if you're not going to be in your house for 10 years, don't bother. You're not going to reap the benefit of this. On the bright side though, once you've done the initial investment of putting this in, let's say your heat pump fails. First of all, the heat pumps are going to last longer than anything that has field connect and refrigerant lines. Because just generally in the HVAC trade, we don't do a very good job with those. It's like a universal problem. We're not great at, the basic thing that we're supposed to be really good at, connecting refrigerant lines. By and large, it's something that is a industry-wide struggle to keep refrigerant lines from leaking. And the refrigerant is what cools the compressors. So if you have a refrigerant leak, you generally are just destroying your compressors. And it can take a long time. There's no way for you as a consumer to really know until it stops working. And by then the damage is kind of done. So with air to water, let's say your heat pump, first of all, your heat pump's going to last longer, but when it does die, we don't have to change out anything else. All this stays. It's literally close two valves, open two unions, carry the old heat pump away, albeit they are heavy, so it's a little more involved than just carrying it away. It's not like you're just one guy's going to go up, I'm done with this now. That's not happening. These also weigh like 471 pounds, something like that. They're quite heavy. But in the grand scheme of things, it's a lot better than like a mini split system, where if you lose your condenser, you get to change out everything attached to it, especially as we change refrigerants. The refrigerants are never backwards compatible.
Curious, what about death of a heat pump? Like, what part of it dies? Is it just
With a mini split?
yeah, or the system?
So they're very different things. On these, it will probably be a compressor and it'll probably be somewhere in the neighborhood of 20 to 30 years out.
Yeah.
On a mini split or a air-to-air system, it's almost always the evaporator coil starts to leak. And that's caused by formicary corrosion, which is a result of the cleaning products that we use in our houses that gets into our air, that winds up on our coil. And in the summertime, those coils, if it's even remotely close to properly designed, stay wet almost all the time. So those detergents, those things in our cleaning products, they don't like die. They stay active for a very long time, and they eat little pinholes in your coils, and your coils start to leak. And then you leak your refrigerant out, and then your compressor dies. Whereas the air to water stuff, all those connections are internal, and because it's a refrigerant to water heat exchanger, you're not going and spraying chemicals in there. You don't have the ability. It's outside. So yeah.
So that's copper corroding in the coil.
It's generally copper corroding in the coil. Yep. Carrier has like a 4-page study on Google you can find that'll teach you all about formicary corrosion. I could get into it, but you guys would all be asleep, and we would definitely miss our curfew.
earlier AC electrical distribution, they discovered this problem, that the insulation around the copper was corroding the copper. So they started silver plating the copper.
Yep. Well, it's aluminum plated, but that doesn't help with the formicary corrosion. Yeah, we don't have silver plating in the HVAC industry because our stuff is already too expensive, and if we start coating it in silver, yeah, I don't want to have to give you a price on that. Yeah, we'll just get it wet, roll it in some diamond dust, and call it a day.
So the equipment is more expensive. You've got a lot more to install, but the efficiencies are significantly higher, and it sounds like the lifespan of the equipment is higher.
Yep.
Josh, have you done?
That is not why you do it.
Have you done the break-even point? Like
Yeah.
Years.
This is my forever home.
For sure.
It's not why you do it.
Yeah.
There's nothing to do about efficiency. It has nothing to do about any of that stuff. It has to do with comfort.
Got it.
Bottom line, I'm going to be there for 20 years. Hydronic is the most comfortable heat you're going to get. There's no moving air. You're not. I have vaulted ceilings for those that were at the house. You saw the great room. I'm not trying to push all that hot air back down and create a draft in the middle of winter when drafts get cold anyway. It's a high performance house. It's going to be super airtight. So for me, it was all about comfort. And I knew that hydronic was going to be the most comfortable. I knew I wanted air conditioning. Jason guaranteed me you're not going to need a dehumidifier. After I listened to him and learned more about how that coil is going to work, the fact that it's not chilled to below freezing like a refrigerant would be, it's chilled to water temperatures that are above freezing, which means you can push low amounts of air over it and dehumidify the air really slowly throughout the course of a whole day at very low energy cost. And dehumidification control is right there in the system design. You can't do that with refrigerants, so that's one reason. But it really came down to dehumidification, comfort with heating, comfort with air conditioning, and that's why it drove all of the decisions that I was making. Payback, it's a lot of money. It's a lot of money.
Yeah.
Well, so there is a payback to it.
There's definitely a payback to it.
Because, well, so think about it like this: is when you're done with if you have an air-to-air system and you have to rip out and replace all your fan coils and your condensers, you're spending, just today, those replacements cost anywhere between 16 and 30 grand, depending on what you're doing. Can go north of that even, depending on the size and what equipment you're speccing out. And in this case, if one of Josh's heat pumps fails, first of all, the other thing is that going back to comfort is, let's say one of his heat pumps fails. He still has heat through his entire house. Not as much, but his house isn't freezing. It's not like with a mini split where if this condenser fails and it does this room, and this room, well, this is dead, so none of these have anything. With an air to water, we're just heating and cooling tanks. And in heating and cooling tanks, those tanks are connected to the whole house. So you might not have, you can decide how you load shed. So you could say, I've got 2 rooms over here that nobody's using. I'm not going to condition these rooms, but I'm going to keep my master bedroom and the kitchen, the living room warm. And I've got the ability to do that. Whereas with mini splits, so I looked at doing the Cambridge Boat Club. It's always going to be the Cambridge Boat Club. They're always going to own it. It's never getting sold. It's always going to be what it is today. We looked at doing air to water there for the benefit of, because they're going to own it when that system expires, when the air to water system we put in today dies, the cost of replacing those components is significantly less, and it means they don't have to close for somebody to come in and rip the building apart and retrofit it again. The only reason we didn't end up doing that was because the ADA got involved, and they were fine with the $500,000 HVAC system. It was the $1.2 million elevator and the other $500,000 in ADA additions they had to do that were the killer. So we didn't end up getting that project because of that. But the point of having it was, hey, we lose a heat pump. We can just unbolt that heat pump, carry it away, put a new one in, reconfigure, 8 feet of piping max, and rewire it, and we're done. We're good to go again.
Ross makes a good point too, that if you want to add to your system,
Yep.
say you have a house and you're like, in 5 years, we're planning to have a family and we're gonna need another room and this and that. Ross is like, you just cut the water line
Add another one.
and add another.
You can splice in another heat pump.
Super easy.
And you don't have to go and mess with anything that's existing in the house. Now, if you're doing an addition, obviously you need more distribution for that addition because there's nothing there already. So you'd have to add that, but you don't have to go and tear out everything that you already have and to make this work. You could just tap onto your existing.
You talking about the like 12 gallon a minute pumps that you've got, which I'm assuming live inside, not outside.
They're inside, yep.
Are they loud?
No.
Okay.
Nope. They're very quiet. Even when we get into like the large commercial grade pumps, they're still very quiet. I have an application in Cambridge where they're right below the breakfast nook, and I can't hear them when I'm sitting up there listening for them, and they're in operation. And that floor is, I don't even think it's insulated. I'm pretty sure it's not. That builder was kind of suspect.
About a month ago,
The mounting makes a big difference.
John Siegenthaler, one of the gurus in hydronics, had one of his monthly, YouTube shows, and it's I think through Enertech, which is another manufacturer of air-to-water heat pumps, but basically he compared price for mini splits and fan coil system in upstate New York, and the air-to-water system was $2,000 less. So, that's some hope that.
I don't know how that's possible because I
it's a
happen
simpler system than obviously Josh's, but
I have pricing on that unit. That's a $22,000 condenser and a $12,000 indoor unit.
well, so Enertech does some things maybe that you wouldn't. They're also on the air to water side. They're using domestic hot water like you are, but on the mini split side, there's a separate heat pump water heater, so you take that cost out.
Yep.
So there's a few things. The way that the HRV was connected to the ductwork, that saves some money, whereas that ductwork was more expensive on the mini split side. But basically, it was $48K for the mini split, $46K for the air to water 5 fan coil system. But it again also included domestic hot water, cooling, and HRV.
You don't need dehumidification, so you can pull out the dehu side of it.
What about operational costs of running those the heat pumps versus the condensers?
So the operating expense is, generally speaking, air to water heat pumps are going to have lower COPs. The numbers that I happen to have committed to memory are worst case numbers. So the Space Pack unit has at minus 22 has a COP of 1.87. Worst case scenario, that's 131 degree output temperature at minus 22 outside. The Samsung, which is my line of mini split that I do a lot of, is 1.49 at minus 13. So it's a pretty significant difference when you factor in both the difference in temperature going minus 22 to minus 13, and then you're also three tenths higher on the air to water. And if you think about that, that's because water is a better heat transfer medium. As an example, everybody here is cooked in an oven, right? And you reach into the oven with just an oven mitt and at 400 degrees, and you pull out whatever you're cooking, and no harm, no foul. Put your oven mitt on, dunk your hand. Don't actually do this. You will go straight to the hospital. This is not actual advice. But if you were to put that same oven mitt on and dunk your hand in 200 degree water, you're going straight to the ER. Don't stop. Don't pass go. Do not collect $200. Straight. One stop. Water transfers heat a lot better than air does. So when we're using water for a transfer medium, we can just hit higher efficiencies. We also don't have to cook stuff as hot to do the same job.
My understanding is Europe, this technology, air to water, has been popular for decades.
Yep.
And why are we so slow to adopt it here?
If you figure it out, I would really like to hear it. Europe also, they have R290, and R290 makes a heat pump a viable boiler replacement with a COP of like 3.5. We don't have that because politicians are stupid. Seemingly all of them. I haven't found a single one who's not stupid when it comes to this stuff. They just, I don't know. Like I said, they become viable, not even viable. They're just really good boiler replacements, and that's not good for the fossil fuel industry. And then politicians can't get rich.
Damn that. So who are some of the equipment manufacturers? I know Taco is getting into it. Warmboard has got their own Lochinvar branded Are you finding?
Everybody has one
availability
now.
is good now?
Everybody has one now. They're pretty much all the same. They're all made by Phoenix. Not all of them, but the vast majority of them. Phoenix makes the Viessmann heat pump. They make the Space Pack heat pump. They make the boiler, the Burnham heat pump. I think they make the IBC and the Lochinvar, but I'm not sure. LG makes their own heat pump. That's not that's actually genuinely theirs. NTI just dropped a heat pump. I think that might be theirs, but I'm not sure. It may be a rebranded version of somebody else. The system, Taco System M, is not actually made by Taco. It's a German company. They just rebrand it. It's also not good for our climate. It's too small. It's a great heat pump. If you lived like in the Carolinas, fantastic product. Just too small for us. They don't have a bigger size.
Sorry, Taco. It was done by Medea.
Is it Medea who does the Taco?
I don't know if on this one thing when I looked up the AHRI,
It would not surprise me in the least.
it was Medea.
Medea makes a great heat pump. I got absolutely nothing against Medea heat pumps.
Well, they make so many different.
Yeah, they have.
Everything.
They're like the biggest white labeler out there. They'll sell anything to anybody. iFlow, the ones that we talked about at the very beginning, the guy who sponsored this, his heat pumps are made by Medea. Bosch is made by Medea. Ecor is made by Medea. God, if I listed every Medea brand, we'd be here all night. There are a lot of them made by Medea. They make a great product, but I haven't seen their air to water yet.
I recently talked to an HVAC guy. They quote an air to water in my house, and he said something that was interesting. He was trying, I think, because of the price, and he probably assumed I was going to balk at the air to water. But he was trying to talk me into air to air, and he was saying that in his experience, the refrigerant lines, at least as his company installs them, never leak. But he always finds leaks in glycol lines. Like glycol always finds a way to leak. Is that?
I mean, I've been working with glycol since like 2005. I haven't seen glycol lines leak. If you going back to like 2008-ish, the first run of ProPress fittings, the rings weren't rated for glycol, so they would weep out, but not since like 2010-ish. Yeah, it's, and if you were worried about that, you could use PEX or you could use polypropylene, both of which are rated for glycol and don't experience leaks. If you pick poor material, if you grab fittings that aren't glycol rated, then yeah, you'll have a problem. But that's why I use fused polypropylene, because you could run straight up acid through that and it doesn't care. Glycol, certainly not a problem. You can't use CPVC because CPVC does not play nice with glycol. It will fracture and crack. Got dragged into a lawsuit in Rhode Island. I was not the installing contractor. I was the guy who said I would go and look at it. And so now I have to be a witness, which is super annoying because you don't get paid for that. Fun fact, you get to go all day to Rhode Island and sit in a attorney's office, but you don't get paid. I wonder if an attorney would come to my office for no pay. Anyways, so yeah, if you pick the right materials, it's not an issue. We've never had a glycol leak in any of the air to water systems I've put in.
So for someone that's downsizing, like let's say an ADU, is that an option for it, or the mini split will be the best option?
It depends on your budget. Mini splits will work. Air to water will work. It'll do. The nice thing about doing an ADU is it'll do your heating, your hot water, and your cooling all in one unit. You don't need to have your mini splits and domestic hot water and standalone dehumidification. You'll just have one piece of equipment, but it is an expensive setup to do. The other thing that's nice is you can always trench lines. So if your primary residence that you're working in has an air to water, you can trench lines and you can feed out to your ADU. So you can use the same piece of equipment as long as you're not trying to separately meter it, have a separate utility for it where they pay their own utilities. You can just pull a set of lines out. and feed your ADU off the existing house, assuming it has the capacity. And if it doesn't, again, you can just cut and tap on a second air to water heat pump in conjunction with what you already have to get yourself the extra capacity.
In that example, though, you've got a lot more physical stuff you're trying to fit in. Is there like a size where you're like, this is too, you know what I mean? You like heating a shed and 3/4 of the shed is full of equipment. And
Yeah, so you're generally gonna so Josh's mechanical is enormous, but Josh has a ton of stuff going in there. I've put these into pretty small spaces. When you get how small?
yeah.
I mean, what's the minimum that you would be able to do? Buffer tank?
I have one on a 6-foot mechanical room. So it's like 6 foot. I have 2 tanks in there. They come off the wall maybe 30, we'll say 3 feet. So 6 by 3 I could get them into. It's not the tightest installation if we've got to go that tight, because you have stuff that you have a lot of stuff. You got valves that need to be on top of each other. It's not the tightest, but I've done it. You can.
What's the dimension of that?
So it was the wall was 6 feet long. The equipment came off the wall about 3 feet, and then the ceiling was standard basement, like a 7.5 foot ceiling. We didn't go all the way up. We didn't need to, but we could have. It wouldn't have tidied the job up any. It was just, when you start trying to, it's like back in the boiler days when you were trying to put a boiler into the room the size of a phone booth. It just gets cramped.
Sorry, can that be into a well insulated crawl space?
You need some height, because the batteries are about this tall, and a buffer tank is somewhere between this tall and this tall, depending on the size.
At least like 6 feet.
So you need some height there. You need at least 6 feet of height, typically. If you're going to do a reverse indirect instead of a battery for domestic hot water, you're going to be looking at probably 6.5 feet, because you got the air separator and you got to have room for the mixing valve. Now, what I've done is I've had them where, the top of the tank is, maybe 3 inches from the rafters, not the rafters, the floor joists, but we just positioned it so that the air separator was in between the bay and, made it work. Mixing valve comes out, comes down, and is at eye level, but the air separator is at the top of the tank. It's sitting up in the bay.
So if you have an ADU of 900 square feet, what would that cost, more or less?
I couldn't even begin to put a number to it without seeing a set of plans. Again, we'd also have to talk about what you wanted to do for distribution. I've got cards out there on the table. If you want to grab one, we're local. We're in Arlington. We'd be happy to set up a visit. We'd come look at it. You can email over plans, and we can take a look at it and give you a number. I'm not going to be competitive with mini splits. I just want to be straight up with you on that, because my material costs more than a mini split job. But it's a good product. It'll last forever. It's going to cut your utility bills. Overall cost of ownership, if you're going to own it for a long time, the overall cost of ownership does pay off, especially when you start to think about replacement costs and what those are going to be in 15, 20 years versus today. You can kind of front load all your costs.
Have you done radiant cooling?
Twice. It's very difficult in this climate. Radiant cooling. So radiant cooling is tough to do because radiant cooling doesn't address, you can't have condensation. So that would be like a chilled ceiling generally is the way we do it. There's a company in Portsmouth, New Hampshire that specializes in it, but it's quite difficult to do in this climate. The last time I did it, the dehumidifier, which is a 4-pipe desiccant dehumidifier, this was pre-COVID, and it cost, if I'm remembering right, it cost about 22 grand to get dropped off at my shop. He needed 2 of them. So it was 44 grand just in raw, like what it cost to buy and have it delivered. No markup, no installation, about 44 grand in materials. So, and that's just the dehumidification. It doesn't cover any of your heat pumps or anything else. So they tend to get very expensive, and they are very comfortable, but we can do damn near as good for a fraction of the money using fan coils.
What's the company in Portsmouth?
Chris, what's the company in Portsmouth?
Thermahex.
Thermahex, there you go. Yeah.
I guess the other thing about radiant cooling is just the basic heat moves from hot to cold, right? So if you heat something, it's going to emanate that heat more efficiently than taking something and then trying to capture that heat, right? It's easier for something to emit it than it is to go gather it and then bring it in the right place at the right times, and being able to do that with the sensitivity of humidity changes and not creating condensation.
Yeah, there's a lot of controls that go into it. If you wanted to do a radiant cooling job, we'd be happy to do it. I would love to do another radiant cooling job, but you got to have a real thick checkbook because it's expensive. Your wallet's got to be pretty heavy.
Of radiant cooling.
It's a cool factor thing. You can say you have radiant cooling, and none of your friends can say that.
I mean, before they had like small duct, high velocity small duct air conditioning. Like think about big duct work. Like if you were really limited on your
Yeah.
duct work in your house, that'd be an option because you're running a small pipe through the walls and then you're getting a big panel on a surface of something that can take it. But
Yeah.
the big duct work, if you can't retrofit it, like a lot of New England houses didn't have air conditioning, and if they had boilers for baseboard radiator heat, you don't have place for duct work. You can't get it around without totally gutting the house.
But even still, especially in New England, your dehumidification system is going to involve a lot of ductwork anyways. So you're still tearing your house apart. There's no getting around it. It's awesome. It is super comfortable when it's executed. It's a really, really comfortable house. You're going to find that you're going to set your thermostat to 78, 79 degrees. It's super efficient, and you'll be every bit as comfortable at like 78 as you would be in a typical house at 74, 73. So you use a lot less energy, but there isn't a payback on that. It's wildly expensive. When we talked to Chris, we talked to Bob, what do you say it was, like somewhere between 35 and 75 bucks a square foot? Was it somewhere like that? Or 35 was like the get you into it introductory rate for like the first job. And I think he said it goes up to like 55 or something after that. And that's just materials. That's not for me to install it. That's just to buy it. I'm pretty sure it was 35 was definitely like the first job gets you into it thing. And then I think he said it went up to 55 bucks a square foot from there.
I'm not sure that include the controls either.
Yeah, I don't think that included the controls either. The controls were another 15 grand is what he told us. So like I said, if you want to do one of those jobs, I'd love to. I think it's super awesome. But you really got to have a heavy wallet to be able to throw one of those together.
Question on cooling still. So like everything here has been fan coils for cooling and radiant heat or radiators for heating. Is there an option to not use radiant means for heating?
Yeah, you can use a fan coil for both. You can use the same fan coils for heating as you can for cooling.
So like at Josh's house, the space packs that are in the rafters.
Yep.
Up in the attic space. Those can do heating and cooling.
They could.
Using them.
In his case, they don't, but his could be configured to do heating, even in his current configuration. They could be set up to do heating, but they're not designed for that. They're designed for cooling. He doesn't have enough distribution to be a primary heat source.
One set of stuff for heating and one set of stuff for cooling.
No.
One set of stuff for
But if you were gonna do air for heat and cool, would you want to use air to water as the mechanism to do that?
Exactly the question.
Would you just do air to air?
Well,
I
can make the argument like I don't want the refrigerant in my house. I like the refrigerant outside.
Sure.
I
That's
like that, I'm gonna add on in 5 years and I know I'm gonna do that. And the system's gonna be there. I just wanna cut the pipe and add it on.
so my house is actually an air to water heat pump, 2 batteries or a buffer tank, depending on seasonality, to an air handler. So I actually do that. I have one zone of radiant in the bathroom, and an addition that we're doing is going to be predominantly radiant. But the rest of my house, my existing house right now, is a duct system for heating and cooling. I did that because I spend most of my day on job sites, not super comfortable because most job sites aren't heated or cooled. And when I get home, I want to be comfortable. So I want my humidity controlled. I will pitch a fit if I get home and my house is anywhere above 50% RH. I will pitch a fit like a toddler and it's not pretty because nobody wants to see a grown man cry. So I have hydronic cooling because I want my house to be comfortable all the time, and I have zero tolerance for it not being comfortable. So that's why I did it.
Hydronic cooling via air.
Hydronic cooling via air, exactly. So what happens, my house is a 1,800-ish square foot ranch in southern New Hampshire, built in like the 60s. Pretty terrible construction, leaky as all get out. So a traditional air-to-air heat pump was not going to be a great option for me because I have zero tolerance for anything higher than 50% RH. So what happens in my house, when my air conditioning coil goes away, when my house is satisfied it's at temperature, my fan will ramp down and it'll push about 200 CFM across the coil, just taking humidity out of the air, just wrenching it out and dumping it outside.
How is it sensing the call for dehumidification versus call for heating or cooling?
I have 3 thermostats in my house that can all call for air conditioning and dehumidification. It's through the,
You have a sensor on the wall.
Yep.
That is both. I'm like moving around.
That is both.
Yep. It says heat, cool, or dehumidify.
It doesn't say, so the dehumidification settings are they're in the deep settings. It's not displayed on the screen. Because I have no tolerance for that, and I don't want any of the other 2 people in my house to mess with. That's like the one thing that it's like a line in the sand. Yeah, I don't, you want to mess with the cooling or the heating temperatures, that's fine.
But that sensor is letting it know that I want you to heat, or I want you to cool, and once those are done, I want you to dehumidify.
Yep,
And it's telling it, when it's heating, give me all you got. When it's cooling, give me all you got, or give me somewhere in between. But when it's dehumidifying, it's saying, just give me a little bit.
So my system's modulating, so I can have, my heating is, I have 3 stages of heat, 2 stages of cooling, and then I have dehumidification separately. So if, let's say my house, my cooling set point.
When you say stages, can you like quantify that? Is that like 600 CFM, 400 CFM, 200 CFM?
What are I know my dehumidification numbers. So I'm roughly 700 CFM in second stage cooling. I'm somewhere around 300 CFM in first stage cooling. And then CFM is cubic feet of airflow, for anybody who doesn't know. Think of it like basketballs of air moving through the ducts.
1 CFM.
1 CFM is about 1 basketball worth of air. So we're moving that much air through the ducts. On high stage is, I think it's 700. I think I'm 300 on first stage, somewhere in that ballpark. Heating was a long time ago, I don't remember, but it's probably semi close to that. And then in dehumidification, I'm only 200 CFM. So it's
and that's something you can't do with an air to air.
Right,
no.
Air to air is not.
You don't get that level of control. So with an air to air heat pump, you generally have to move that. The number that's generally accepted is 400 cubic feet of air per minute per ton. That's not a right number. I specifically target more like 350, 325, but you can't get much lower than that 325 threshold before you'll start to freeze your indoor coil, because refrigerant is harder to control temperature than water. So like any one of these tanks, if I want this tank, or this is my cooling tank, if I want this tank to be 44 degrees, I run my heat pump until the tank's 44 degrees and then I shut it off. But with refrigerant, I can turn down my compressor, but refrigerant isn't as controllable. It reacts to pressure more, and I can't control it nearly as finely as I can control water temperature, right? I can control pressure, which sort of translates to temperature, but not exactly. So I need to move a minimum amount of air, or I'm going to freeze my coil on a refrigerant-based system.
And is it always below freezing?
Refrigerant, if you don't do anything with it, if atmospheric pressure, refrigerant boils at like minus like 14 or something like that.
It's always really cold.
It just naturally wants to be really cold when it's under pressure, when it's doing things. It absorbs heat really well. But the downside of it is you will literally, when I say freeze your coil, I literally mean your coil your indoor unit will look like an ice cube. I have seen technicians like chip away at it. Horrible idea. Don't do that. It's a bad idea. But I've seen it happen. They will literally chip away at it with like a hammer and a flathead, or they'll get their torch out of their truck, and all of these are bad ideas. You shouldn't do any of these things. But I've seen all of these things done. I mean, you stay in the trade long enough, you see some like, that is a creative way to do something really stupid. Congratulations, you win. You will see this stuff, and so with water-based stuff, we don't have to worry about. We're not going to a 44-degree coil will never freeze, so we don't have to worry about that. And so I could technically have a 44-degree coil and have zero airflow, and it's never going to be a problem. Whereas if you cut your fan off even for a minute or a couple of minutes when your condenser is running, you will freeze your coil right up. It will start to form ice on it. The moisture in the air, that coil will get below freezing. The moisture in the air will freeze on the coil. And once that starts, it just grows until the whole thing is a sheet of ice.
And when your filter is cake, and that's another way that you can restrict your airflow, is just from lack of maintenance. Your filter builds up, it restricts the airflow, then the coil freezes. And then they're like, what happened to all this? And then it's a whole thing.
Well, you gotta change your filter.
I can't tell you how many times I've walked into somebody's house, found a frozen coil. Sir, ma'am, where's your filter? I have a filter? That's your problem. I figured it out. And then you pull it off and you can't tell if it's the filter or the family cat. It's one of them, who knows what. They're just atrocious. So with the water systems, at least we're not going to freeze it. It's not going to work. If the coil looks like your cat, it's not going to work. But you're not going to freeze anything. You're not going to have to worry about water damage. Nothing like that's going to happen. So that's why I did it, because I wanted the comfort of the dehumidification, and I like the idea. I get better efficiency out of an air to water running a lower water temperature through a fan coil than I would with an air to air heat pump. At worst, I think my efficiency, my COP is like at minus 22. I think I'm still like a 2.5 for COP, which is better than what you're going to get as a. Totally lost my. What were you showing me?
Sensible heat ratio.
Sensible. Oh, we'll touch on sensible heat ratio. I'm trying not to get that nerdy with it. I feel like I've already like expended my allowance for nerdiness today.
Well, on that note, we should probably wrap up and have a few minutes to chit chat and mingle before it's.
Peter, I think
Fantastic.
one thing, though, Peter, if I could, when you were mentioning, like, yes, you could do air to air, right? You could use air, but I think, at least for me, for me, it's understanding the value of using radiant versus air as a heating mechanism.
Yep.
I mean, and if you're trying to compare like the benefits of heat pump to get air versus a forced air system, that could be on natural
The level
gas
of
or-
comfort that comes with a radiant system versus an air system is
and it's very tough to quantify.
in a different.
How do you quantify that to anybody, right? Like, how do you explain?
Well, that's why, like, how this all happened, right? It's like, Ross really likes air to air. Why does Ross really like air to air? Because this client has a shit ton of money.
Ross likes air to water.
What?
Ross likes air to water.
Air to water.
I was confused as hell for a second. I was like, wait, when did that happen?
Why are they putting all these? He does air to air too, but because the clients are very discerning, right? Like,
Yeah.
you want the best, but only like, $10 million house a month, like that's what comes with that territory, right?
So
But it doesn't mean that you can't put these in other houses.
with an air to water to air, I can still get a really, really, not as good as a radiant house, but I can get a house pretty damn comfortable because I can control airflow. And if I distribute it properly, I can use that airflow to raise the mean radiant temperature in the space, which is the average temperature of the things around you, which makes up the majority of your comfort level as a human. If everything around you is warm and radiating heat off, you're going to feel warmer than if the air around you is warm and everything around you is sucking up heat. So if we distribute the air well, and high velocity lets us do that because there's small ducts, we can pretty much put them wherever we want. And we can distribute that air really effectively, and we can raise the mean radiant temperature of the surfaces in the space and make the house really comfortable. Not as comfortable as a radiant floor house. When I was designing my system, I toyed with the idea of ripping up my floors for about 15 minutes. And then I was like, this is I have nice floors. I don't want to get into this. This is like the only good thing of my house when I got into it was the floors. I was like, if I tear these up, I'm probably going to be single. That's problematic. So
Also, with a heat pump for heat and like ducted heat via heat pump, and it's modulated. It's a it's like a steady, constantly running at a lower level.
Yep.
Versus kind of an older forced air that's going to blast and then shut off
Yes.
and blast. So the discomfort is probably less.
Yeah, we get a lot more comfort. Again, it's not a radiant floor house, but it can be pretty damn close. And it can be done, if we're doing it that way, it costs a lot less money to do. It's like anything. If you wanted, if you buy your car with every bell and whistle, you're going to spend more money on it. If you're okay with, standard seats, not the heating, cooling, massaging, all the other stuff that the seats do these days, you spend less money on your car. You don't have to have the biggest engine. You save money. These are all the things. It's the same as buying a car. If you want all the bells and whistles and you want the super fast version, you pay a lot of money. And if you want the more modest version, you can get the job done for less. We're probably never going to be competitive with mini splits in the air to water game, but it also doesn't have to be a $200,000 job. I've done them for 60, 70, and 80 on plenty of occasions. They're still not cheap, but they can be done. I think that I did one last summer in Lexington. I think it was like 52. That's the cheapest I've ever done one. So they don't have to be, 52 is still wildly expensive if you ask me, but,
52 for air-to-air systems all the time.
yeah, I've seen plenty, I've competed with plenty of, depending on what you're doing. My $52,000 air to water was pretty small, but, they don't have to be, you don't have to be a billionaire to be able to do them, but you're not going to be competitive with at least in the initial investment, you're not going to be competitive with a mini split doing air to air or air to water.
Let's wrap it up.
All right. Thank you.